Welcome back to MH Science. In the previous video, we explored the first atomic bomb, Little Boy. You can check out that video on our channel to learn how Little Boy works. In this video, we will discuss the improved design of the second nuclear bomb, named Fat Man. Fat Man was dropped on Nagasaki, Japan, on August 9, 1945, 3 days after Little Boy destroyed Hiroshima. The size is about 3.3 meters in length, and 1.5 meters in diameter. The weight is approximately 4,670 kilograms. The Fat Man bomb uses plutonium-239 as its fuel. Plutonium is a fissile material that is capable of undergoing fission reactions. Nuclear fission is the process in which the nucleus of an atom splits into two or more smaller nuclei. Plutonium-239 has 145 neutrons and 94 protons, giving it a mass number of 239. Fission begins when a low-energy neutron, known as a thermal neutron, is absorbed by the plutonium nucleus. The plutonium nucleus becomes unstable and splits into two smaller nuclei, xenon and zirconium. Apart from that, it also releases 3 neutrons and energy. This energy is in the form of heat. The equation for this fission is as follows. The 3 neutrons released can collide with other uranium nuclei, causing them to split and release more neutrons and energy. This creates an exponential chain reaction, which results in a powerful explosion. Plutonium-239 has a larger explosive yield compared to the uranium-235 used in the Little Boy. The Little Boy used a gun-type design to convert the fuel from subcritical to supercritical. A subcritical mass is a mass that does not have the ability to sustain a fission chain reaction. By calculating the mass and shape of the uranium, any spontaneously emitted neutrons are likely to escape, preventing a chain reaction from occurring. A supercritical mass, on the other hand, is one where, once fission has started, the reaction will proceed at an increasing rate. A supercritical mass is required during detonation of nuclear explosion. A material like uranium and plutonium can be converted from subcritical to supercritical by altering its shape, density, purity, or temperature. So, for safety purposes, the fuel must be kept in a subcritical state to prevent accidental detonation. However, the problem with plutonium is that the spontaneous fission rate is too high. If plutonium were used in a gun-type design, the fuel could explode early before complete assembly, potentially damaging the weapon prematurely. Hence, no chain reaction occurs. This phenomenon is called a fizzle. To avoid a fizzle, the projectile plutonium would need to be accelerated to a speed of at least 910 meters per second. To achieve this speed, the gun tube needs to be extended. However, this longer tube is not efficient because it is difficult to load into bomber aircraft. Besides the gun-type design, the other option introduced was the implosion type. In the implosion type, a spherical shape of subcritical plutonium is used. The spherical shape is the most efficient for utilizing a chain reaction. During the subcritical state, any spontaneous fission neutrons are likely to escape due to the less dense plutonium. Hence, no accidental chain reaction will occur. During detonation, the plutonium sphere is compressed to make it denser. It becomes supercritical as the neutrons are more likely to collide with the nucleus, rather than escape because denser plutonium has nuclei that are closer together. Hence, a chain reaction will occur. To compress the plutonium, the idea was to use layers of explosives. This is why it is called an implosion-type design. The challenge was to create a uniform implosion wave to maintain the spherical shape in a supercritical state. If the explosive's detonators are placed randomly, the implosion wave will not be uniform and might damage the sphere. Hence, supercriticality does not occur. Therefore, it is important to create a uniform explosive wave to compress the sphere to a supercritical state. To see how to solve this, let's dig into the Fat Man components. To understand the design arrangement, we will start with the innermost component. The innermost component is the polonium-beryllium initiator. Then, it is surrounded by 6.19 kilograms of plutonium-239 fuel. Its diameter is 92 millimeters, approximately the size of a softball. The next layer is the uranium-238 tamper. Then, there is a boron plastic shell. Next, there is an aluminum pusher. Then, it is surrounded by 32 segments of explosive composition. Each segment has a detonator, faster explosive and slower explosive. This symmetrical arrangement of 32 segments is called a truncated icosahedron. This shape is commonly found in soccer ball designs. Then, it is encased in a duralium encasing. This assembly is called a physics package. The Fat Man was carried by the B-29 Superfortress bomber aircraft named Boxcar. The bomb was dropped above the targeted area, Nagasaki. During free fall, a barometer is used to measure ambient pressure and altitude. An altimeter radar is also used to calculate the bomb's height from the ground. The bomb was designed to detonate approximately 500 meters from the ground. When the barometer and altimeter radar measure the correct height, the firing mechanism is activated. Behind the physics package, there is an instrument plate that consists of radars, baroswitches, and timers. In front, there is an X-unit plate that consists of batteries and a firing switch. When the firing switches are activated, electrical charges are sent to all 32 detonators simultaneously through wires. To understand what happens next, let's look at the cross-section of the physics package. Here you can see the detonator, faster explosives, and slower explosives assembly. When all the detonators explode simultaneously, you can see each explosion wave propagate in a convex shape within the faster explosive. Within the cone-shaped slower explosive, the wave begins to become concave. Finally, the 32 waves merge into a single spherical implosive shock wave that hits the inner charge's faster explosive. The wave then hits the aluminium pusher, which is used to minimize turbulence. So, this is how the faster and slower explosives manipulate the wave speed to form a symmetrical implosion shape. Next, the plastic boron shell is used to prevent pre-detonation of the bomb by stray neutrons. The implosion will compress the uranium-238 tamper, subcritical plutonium, and polonium-beryllium initiator. Let's see the implosion once again. The implosion symmetrically compressed the plutonium to twice its normal density, making it supercritical. The compression also crushes the polonium and beryllium initiator together to release a burst of neutrons. These neutrons will initiate the chain reaction. The uranium tamper is used as a neutron reflector to prevent neutrons from escaping, thereby enhancing the supercritical state. The tamper itself undergoes fission, producing up to 30% of the weapon's yield. And finally, a powerful nuclear explosion occurs. The detonation released the energy equivalent to the detonation of 21 kilotons of TNT. Compared to the little boy bomb, which used 64 kilograms of uranium to produce 15 kilotons of TNT, the Fat Man is more efficient, as it only uses 6.4 kilograms of plutonium to produce 21 kilotons of TNT. That's all for this video. Thank you for watching. Please subscribe and like our channel. See you in the next video.